We'll move now into solving problems where we have more than one dimension along which an object can move. So we have two-dimensional kinematics problems at this level. Further in physics, you might do three-dimensional kinematics problems, and really the process isn't much different. The heart of these problems is understanding that what happens in one dimension won't have an effect on the other dimensions. So for example, if we have some object that's accelerating in the y direction, that isn't going to cause a change in velocity in the x direction. Or if it were accelerating in the x, that wouldn't change any change in velocity in the y direction. We call this idea the principle of independence of perpendicular motion. So again, what happens in the x direction stays in the x direction. It's like Las Vegas. So we end up splitting up a two-dimensional problem into really two separate one-dimensional problems. Now there are some issues with this, namely that we have a lot of variables to deal with, so organization is important. We also have some vectors that we're going to have to handle, maybe some vector resolution or combining components of vectors to make a single vector. So we do combine some of the stuff we did with vectors with some of the stuff we did with one-dimensional kinematics. But once we understand how to combine that, there's really no new material here. It's just a combination of two things we've already done. So let's get started. Before we get into much in the way of calculations or vectors or any considerations like that, we want to understand the situation, so we'll read through enough to know what's going on, and then we're going to have to define what coordinate system we want to use. This is important in one-dimensional kinematics too, but now we have twice as many axes, so I don't know, twice as important. We can define our x and y axes however we want, so long as they are perpendicular to each other. Further on, there's also a requirement that they would follow something called the right-hand rule, but we don't need to get into that for now. So as long as x and y are axes that are perpendicular to each other, we're okay from there. So we're used to having x be horizontal and y be vertical, and that might make sense if we have, say, a situation where maybe we have a ball that starts at some position we're calling the origin, and we give it some throw up this direction, and it travels along some curved path back down to the level that it started at. Horizontal and vertical makes a lot of sense there, in particular because it's going to be accelerating downward due to gravity. We would want one axis, or it's convenient to have one axis that's parallel to that direction. So here the acceleration is all in the y direction. So up and down for acceleration left and right, we wouldn't end up having acceleration there. That's convenient. Anyway, we've defined an axis. That's a good first step. We might also have these tilted. And one situation we'll see frequently is if we have, say, a ramp, and then our object is on the ramp and maybe sliding down this direction. It'll often be convenient there to have one axis that's parallel to the direction of the ramp and one that's perpendicular to the ramp. So there, for example, could make x be along the ramp and y be perpendicular to that. So we'll explore that system more later on. For now, we're pretty much going to say x is horizontal and y is vertical. As far as our variables and equations go, we had one axis before along which things could move. Now we have two. Twice as many axes is going to mean twice as many variables. Well, almost. And twice as many equations. So now to define, say, starting position completely, we can't just use the x position. We have to use the x position and the y position. Ending position has two coordinates as well, the x part and the y part of that position. Starting velocity, that could have an x component and a y component. Ending velocity could have an x component and a y component. Acceleration can be in the x direction and the y direction. Time is not in either of those directions. When you ask somebody how long it took them to tie their shoes, odd question to ask, but if you asked it, they wouldn't say, oh, 5 seconds to the right or 10 seconds south. No, it's just 10 seconds, 5 seconds. There's no direction with that. Time we treat as a scalar quantity in all of these, and so as a result, we don't have two separate times. There's no time in the x direction or time in the y direction. It's just time. As a result, we can use that value t in either our x equations or our y equations, or both. And so that tends to act as a bridge between our x information and our y information. Now, as far as the equation goes, we've doubled the number of equations simply because we've rewritten each equation with all the x's being replaced with y's. So every time I have a subscript x, or every time I have an x by itself, that has been replaced by a subscript y or a y by itself, respectively. Those new equations aren't on the equation sheet because there's really no difference there. It's just all the x's have turned into y's. If we had a third dimension, we have a third set of equation with z's instead of x's or y's. If we had a fourth spatial dimension, well, we're out of letters. We'd have to go back to the beginning. I don't know. A's, the A dimension, why not? We'll stick with 2, so don't worry about any fourth dimensional projectile motion thing. That's too much. So with these two equations, we'll notice that there isn't any, or these two sets of equations, we'll notice that there isn't any overlap of x's and y's. This equation has all x variables in it and time. This one has all y variables and time. All x, all y. All x, all y. So we're never going to mix and match x values with y values in these calculations. Now, the only other piece that we have to worry about here is sometimes we'll be given values that aren't in the x direction or the y direction alone. They might be at some angle between those two directions. So we might have to do some vector work, some vector resolution in order to make this work. So we'll get a taste of that and how to use all these equations together in our very first example. So here it is, our first projectile motion problem. This is going to be two-dimensional kinematics. Projectile motion, we have one more piece that goes into that. Projectile motion is motion of an object that changes because gravity is acting on it, but no other forces are. So we're not talking about airplanes with jets and wings providing thrust and air resistance. We're talking about maybe a ball or a bullet moving through the air, something that doesn't get propelled forward or upward, no lift to it. So it's flying through the air and it's going to follow a curved path back toward the ground. So here we have a toy car going off a 1.5 meter tall counter at a speed of 3.0 meters per second. So it's driving off horizontally and then it's going to fall downward. So I can tell already this is a two-dimensional problem because there's left and right motion, or forward and backward motion, and then there's also up and down motion. So I'll go ahead and set up my list of variables for two-dimensional motion problems. Now, question A asks us to figure out how long it's going to take the car to reach the floor. And so that actually gives us a couple pieces of information. First off, it tells us that the car is going to reach the floor. So we have an ending position. We also know something about the starting position. It starts on the counter. And so we'll need to define those positions numerically. We're told that the counter is 1.5 meters tall, so I'm going to make my initial position a positive 1.5 meters, and my final position 0 in the up and down direction, in the y direction. I could also do 0 and 1.5 if I wanted to make down the negative direction, or I could do 0 and negative 1.5 and still have down be the negative direction there. So you have some options on these things. 1.5 meters above the ground and then 0 meters above the ground just makes some intuitive sense for me. It also tells us that we're looking for how long it takes. Now, how long could be a distance question, but I think we understand this is a timing thing. How long does it take? 2 seconds. That is a reasonable answer. How long does it take for the car to reach the floor? 2 meters. That doesn't seem to fit as well with this question. So we are looking for time in part A. Now, what else do we have? First off, it tells us that the car drives horizontally off of this counter at a speed of 3 meters per second. So it's driving horizontally. That's the x direction and has a speed of 3.0 meters per second at the very beginning. Also, we get to choose our coordinate system here. So our x coordinates, we get some say in what those start at. Let's say that the x-coordinate when it leaves the counter is 0, and that it's going to be moving in the positive direction, because we have that positive 3. So we know that its final position is going to be some positive number. We don't know what the number is, and it turns out we don't care what that number is on this problem. Let's see, for the y direction, we also could talk about initial velocity there. The toy car drives off horizontally. So what's its vertical speed there? It doesn't have any, 0. It's not moving up, it's not moving down for that first instant. But then it starts moving downward. Why does it move downward? Because gravity is pulling on it. Now, if gravity's pulling on it, we know that the acceleration must be that number we use for acceleration due to gravity, which is 9.8 meters per second squared, and that's downward. In the y direction, I'm saying downward is negative here, so negative 9.8 meters per second squared. Okay, almost done now. How much does gravity pull something to the left or to the right? Well, that's a silly question. We know gravity doesn't pull things to the left or to the right. Gravity pulls things downward. And since a projectile is something whose motion is affected by gravity alone, that's the only force that could cause acceleration. So we cannot then have any acceleration in the x direction. Acceleration must be 0. Now for this situation in reality, we would have some air resistance. We are ignoring air resistance unless told to do otherwise, though, for the conventions in this class. And it turns out we can't solve this one with your math backgrounds, or mine for that matter, if we do account for air resistance. So no acceleration here because no air resistance, no other forces except gravity. Gravity only pulls downward. Now that has a consequence for velocity. If it's not accelerating in the x direction, the velocity must end at 3 meters per second, just like it started at 3 meters per second. Okay, now we have all of our given information in. Let's look for the time. Part A, how much time, how long does it take to reach the floor? So I want to think through those 3 kinematics equations and the 2 different variations. One for the x-coordinate stuff, one for the x-dimension stuff, one for the y-dimension stuff. And on this one, you can go through a few of them before you find the right one. In the x direction, we don't have any equations that end up being fruitful for us. So you might look at that combination of variables and think something like, oh, this equation Vx equals Vx naught plus Ax times t. That one we know everything in there except for time. And you're absolutely right, we do, except acceleration is 0. So this equation doesn't end up having time in it. That equation is final velocity equals initial velocity, which we just talked about. We already knew that one. So that doesn't end up being a useful quantity. The other equation that you might look at is the Vx squared equals Vx naught squared plus 2a x minus x naught, and that has the same problem. Plus an additional problem that time doesn't appear in that equation. So we're out of luck there. The last equation has an x in it, a final position, and we don't know that. So we're out of luck on the x side completely. Scratch that. Let's take a look at the y side. I don't know the final velocity in the y direction, and for part A, I don't need to know it. So I'll look for the equation that doesn't have final y velocity in it. And that equation is going to be the one that says y equals y naught plus vy naught t plus 1/2 ay t squared. Now, here I know everything except for time, and so I can solve for time here. Y is 0. Y naught is 1.5 meters. Initial velocity, the Vy naught is 0, so 0 times t is just going to be 0. Plus 1/2, acceleration in the y is negative 9.8 meters per second squared times t squared. Now we'll simplify this and solve for t. So we'll have, let's see, 0 equals 1.5 meters. 1/2 times negative 9.8 is going to be negative 4.9, and the units on that are meters per second squared, and then times t squared. I'll subtract the 1.5 from both sides. Negative 1.5 meters equals negative 4.9 meters per second squared times t squared. Divide both sides by negative 4.9 meters per second squared, and that gives me 0.306. And thinking through the units, I'll have meters divided by seconds squared. And if I'm dividing a fraction, I can just multiply by the reciprocal. So that's the same as meters times seconds squared over meters, which is the same as seconds squared. And that's equal to t squared. And then square rooting both sides gets me 0.53 seconds equals t. Takes a little more than half a second for the car to hit the ground. Now for part B, we're asked for the car's velocity just before it hits the floor. So we're not looking at what velocity it has after it bounces, anything like that. Just before it hits the floor, so after it's been falling for 0.53 seconds. Now, this question does not ask us for the x component or the y component of velocity. It asks for overall velocity just before it hits the floor. So we're going to need to solve for both the x and the y components, and then do a little vector work to figure out the overall velocity. We already have the x component, so all we need now is the y component of velocity. So let's solve for that now. The y component of velocity we'll solve for by doing vy equals vy naught plus ay times t. The vy is what we're looking for. Initial y velocity was 0. Acceleration is negative 9.8 meters per second squared. Times t squared, times t, which is 0.53 seconds. And so our final y velocity then, negative 9.8 times 0.53, that gives us negative 5.42 meters per second. So meters per second squared times seconds gets us meters per second, no more squared. All right, we want the overall velocity, the vector velocity here. So we have both an x and a y component at this point. We have the x component is 3 meters per second in the positive direction. The y component is 5.42 meters per second in the negative direction. So let's sketch this out. We have 3 meters per second in the positive x direction. From there we have 5.42 meters per second in the y direction, the negative y direction. And we're going to look for the overall velocity in red here, v, and we'll need to define this angle theta when we do that. So 2 steps to getting this one figured out. We'll do Pythagorean theorem to figure out the magnitude, and we'll do a little trig to figure out the direction. Pythagorean theorem on this one will say v squared, the magnitude of that velocity vector, is going to be equal to 3.0 meters per second squared plus 5.42 meters per second squared. Include the negative sign there if you want. It gets squared anyway, so we lose the negative sign. Square those both, add them together, and then take the square root, and we'll get an answer of 6.2 meters per second. As for the direction, I see in that diagram, I know the 2 legs of the triangle, the lengths of the 2 legs of that triangle, and this would be a right triangle. The 3 is all in the x direction, the 5.42 is all in the y direction, so that makes that a right triangle. So we can use trig functions on this. I have the 6.2 meter per second hypotenuse, so actually I know all 3 sides. I could use any trig function. I'll use tangent on this one. Tangent of theta is equal to the opposite side over the adjacent side, 5.42 meters per second over 3.0 meters per second. I want theta all by itself, so I'll do the inverse tangent of both sides. So theta equals the inverse tangent of 5.42, and the meters per second appear on top and on bottom, so those will just cancel out, and leaves us with a unitless quantity on the inside. Good time to check here that our calculator's in the mode we think it's in. I'm going to report this answer in degrees, so I'm going to double check that the calculator's in degree mode, and then enter this calculation, and I get 61 degrees. And so last thing we do on these is we state the velocity vector all at once. The final velocity as a vector is 6.2 meters per second at 61 degrees, and let's call that below horizontal. Typically on these problems, we'll have a little vector work either at the beginning or at the end of the problem. Could be both. At the beginning, you might be given something like a velocity that's at some angle. And so maybe we have a velocity that points up like this to begin with, and that's 10 meters per second instead of the car going off horizontally. So then we could break that up into its components, and we'd have the x velocity and the y velocity there. So we might have some vector resolution at the beginning. Here we found components first and then had to solve for the overall vector, but typically there's going to be at least some vector work in these problems. So be mindful of that, and be careful that if they give you something that isn't in the x direction or the y direction, we can't represent that as an x quantity or a y quantity. I couldn't put in this example over here, I couldn't put 10 meters per second as my x velocity, because my x velocity is going to be something less than that, and my y velocity is going to be something less than that as well. I'll have to figure out each of those separately before I can do any of that work. Keep your x's with your x's, keep your y's with your y's. Remember, time is a bridge here. It can apply to x or y, and just keep working through these ones. Lots and lots of practice on these is all it's going to take.